so we're going to get going. So it's my pleasure to introduce today's speaker, Mark Hogan. You know, to me, Mark has just been a staple at SLAC ever since, you know, I joined the lab. To me, it feels like a while ago. I know there's people in the audience who have been here a really long time, but you know, Mark's just a very recognizable figure, and we actually spent some cold, dark nights together over in the FFTB area in the early 2000s. Mark earned his PhD from UCLA, and in 1998 he joined SLAC as a postdoc and has basically been here ever since. And he came here to conduct advanced accelerator research using plasma Wakefield effects to really accelerate particles with a huge gradient. And in 2000, he became the spokesperson for the SLAC plasma Wakefield program. And currently, he is the leader of the plasma group in the FACET division. And in this seminar, Mark's going to tell us the full story of the plasma Wakefield program, the past, the present, and the future. And so please join me in welcoming Mark.
Thank you, Dave. It's funny because Dave and I spent a lot of time in the FFTB in the early 2000s, and that's when I was a postdoc, and I remember having a conversation with my wife when I came here to do this work. I thought, well, honey, I don't know, it's going to be a few experiments, and I'll have to find a job, but surf's been up ever since. So I'm going to walk you through the history of first of all, what it means to be accelerating particles on waves of plasmas and why we think that was interesting back then and why it continues to be interesting, and we're still pursuing this work here at SLAC. So first of all, just embracing Chi-Chang's challenge that I want this seminar to be accessible to anyone at the lab. Let's spend a few minutes and make sure we're all on the same page and speaking the same language. So first of all, what is a particle accelerator? Obviously, imagine if I take a battery and hook it up to two metal plates, I'm going to get an electric field between those plates, and if I then take an electron and let it go inside this electric field, it's going to head away from the negative terminal, head to the positive terminal, and it's going to pick up speed as it crosses that gap. And if the gap is 1 meter, we would say that the electron gained 1 electron volt in a meter. Now, accelerators like the SLAC linac look a little bit different, but it's sort of the same. You have a bunch of pillbox cavities which have been put together with a hole in the middle so that the beam can pass through. Except now in the SLAC accelerating structures here, the electrons gain energy at a rate of about 20 million electron volts per meter. So not bad. Now, you might be wondering, why am I talking about energy instead of velocity or speed? That's because a long time ago, Einstein in the special theory of relativity told us that the speed of light is a fundamental constant in the universe, and you cannot go faster than the speed of light. And one of the consequences of that is captured by this expression here, that what starts to happen is very quickly these particles are going as close to the speed of light as you'd ever hope to measure, 0.999997 the speed of light. And what starts to happen is they approach the speed of light, their mass starts to increase. And what that means is that before you could ever give the particles that last little push to get them up to the speed of light, their mass is going to be so infinitely large you just can't do it. And so we actually say that as their mass increases, the energy stored in these particles is increasing. So we don't talk about the velocity of the particles we produce in an accelerator, we talk about the energy that's stored in each individual electron. And that's important because if we want to use these accelerators as microscopes or probes to understand what the universe is made of, it's important to understand what sort of energies we need to do that. So, of course, matter, the universe is made up of stuff. Stuff's made up of atoms. Atoms, probably most of us are familiar with this picture that there's a positively charged nucleus with negatively charged electrons flying around the outside. And if you want to pull all the electrons off the atoms and understand that structure, you're going to need energies of about 1,000 electron volts, or 1 keV. If you want to look deeper and now start to look inside the nucleus and separate the protons from the neutrons, you're going to need energies on the order of about 1 million electron volts. And now if you want to go deeper still and actually pull apart the structures that make the protons and neutrons up and understand the quark structure inside, you need energies of about 1 billion electron volts. And that's actually what set the scale for the accelerating structure at SLAC and why it is so big, why it's 2 miles long. Because back in the 60s, 50 years ago, these guys knew, okay, fundamentally we can add energy to the beams at this rate, and if we want to study these structures, we need this energy, so we need thousands of meters to do that, and that's why the accelerator is as big as it is. Now, if you look at the history of accelerators, there's something that's very similar to the Moore's law for semiconductors that most of you have heard of. Now, Moore's law is something that says that the density of transistors on a semiconductor chip has been doubling almost every 2 years. And what that means is that you have this exponential growth in processing power, so that now you can do in the computer on your phone what used to take a warehouse-sized computer to do. Or conversely, if you take a warehouse and fill it with the same computing power you have in your phone, you can do things that weren't even imaginable many, many years before. So there's a curve here which plots the energy attainable by particle accelerators versus time, and you can see that over many, many decades, that energy indeed has gone up continually by factors of 10 over and over and over again. And what this curve also shows is each individual black dot is a machine that's existed and operated somewhere in the world. But these red bands that are connecting some of the dots are families of technology. And so what you can see is that accelerators today are not like the ones that we had 60 years ago. That constantly people are pushing and trying to develop what are the new technologies that are going to allow us to keep progressing on this curve and allow us to keep getting to progressively higher in energies. There's always technology from before, and we have to keep looking what's the technology that's going to allow us to make the next big breakthrough. And that's important because we now have this beautiful picture of the universe of how it works called the Standard Model of Particle Physics, which captures the particles and the forces of the universe and how they interact and behave. And that's really in large part due to the fact that we've been able to probe and test these theories in controlled experiments in the laboratory using directed beams produced by particle accelerators. But there's still questions to answer, and we'd always like to keep pushing this curve upwards and onwards. So a little more immediately, a lot of you have probably read in the news that the Higgs boson was discovered at the LHC, and the next big machine that people would like to build to understand this is a machine called a linear collider. Well, it turns out SLAC operated the only linear collider that's ever operated in the world. This was the 3 kilometer long SLC, the SLAC linear collider. It collided 2 beams of 50 GeV, and at that time studied one set of questions. But now to answer the questions that people want to answer, we need to get to energies that are much higher. So even though we have this fantastic 3,000 meter long linac, it's just not enough to get us up to energies we need to answer the questions of high energy physics. And in fact, the different designs that people are talking about for these machines are tens of kilometers long. So these are fantastically large instruments. And really, that size is dictated by how long the accelerator has to be to get the beams up to the energy we wanted. And this is really limited by the accelerators themselves. And so that's one of the reasons why we think it's time for new accelerating technologies and why plasmas might be the answer. Now, you may also know that even though we don't study particle physics at SLAC anymore, we don't use the linac to do particle physics anymore, that does not mean that there aren't still uses for these high energy beams. In fact, there are equally fantastic applications where once you have these high energy beams, you can use them to power devices called a free electron laser, and that's what the LCLS is. If you don't know how the LCLS works, imagine that I've got an accelerator that makes this high energy beam of electrons, and then I pass it into a special device called a magnetic undulator, and then the particles shake back and forth, and as they shake back and forth, they give off their energy and radiation. And it turns out, if you look at the wavelength of that radiation, if I want to get to very short wavelength light, so not visible light, but something that's going to let me take pictures of atoms and molecules, I need X-rays. And to get X-rays, I need to have beams that have very large energy, where that factor of gamma is over 10,000. So that's why I need this very long linac to make these very high energy beams for the LCLS and what will eventually be the LCLS-II. Now you may be asking, if you were paying attention, well, why don't we just make the machine circular? Why don't we just build an accelerator, kick the beam, bring it back around, kick it again, again, again? Why don't all accelerators look like that? Well, some do, but it turns out if you want to accelerate electrons, at some point this runs into problems, and that's because what happens is electrons don't like to be bent. Bending them in a circle is actually accelerating them, and as you do that, as you curve them around in a circle, there's something captured by this expression in Larmor's formula that they start to dump that energy off. So you work really hard to put energy into the beam in this little accelerator, and by the time you bend it all the way back around again, it's given off more energy than you ever put into it with this accelerator. And this power to the fourth down here, what that means is if I now increase the energy by a factor of 10, the beam's going to radiate 10,000 times more strongly. So each time I try and go higher and higher in energy, very quickly this becomes a losing proposition. So what we'd really like is the ability to boost the energies of the particles up and do it in a straight distance without bending them around in a circle. So that means we have to boost the energy up really quickly, really strongly, so that the accelerator itself is a finite distance. So there's actually several groups at SLAC that are working on different flavors of technology to allow us to do that. There's groups in Sammy Tintauri's group that are looking at how can we fabricate structures that are made out of metal with new geometries and new power sources to get gradients on the order of hundreds of megavolts per meter. Joel England gave one of these Science of SLAC seminars a while back where they're using tiny structures which are fabricated using lithography on microchip size and powering them with lasers from the telecom industry to get fields on the order of a gigavolt per meter. And then finally what we're going to talk about today is powering structures inside a plasma with particle beams where we can get fields more than 10 gigavolts per meter. So just to make sure again that we're all on the same page, what is a plasma? So a plasma is something, imagine I have a solid and I start heating it up. Solid melts to a liquid. I keep heating the liquid up, eventually the liquid boils to a gas, and now if I keep heating the gas up, eventually the electrons pull off of the atoms, and what you're left with is this sort of electrically charged soup that has positively charged ions and negatively charged electrons all swimming around together. And now if I can separate those electrons and those positively charged nuclei in a controlled way, in this case with a wave and a plasma, I can get huge electric fields between those two, and I can use those fields to accelerate particles. So really what we're talking about is changing from a paradigm where the structure is fabricated, in this case out of nickel or copper and some block of monolithic material that sits on a girder, to a structure which is created dynamically inside a plasma and it looks like a wave. And now instead of structures that are characterized by length scales of meters, I'm talking about structures which are millimeters in extent but much more powerful and boost the energy of the beams that much more strongly. And so what that looks like in practice is, imagine I have this plasma which is again electrically neutral, all the particles are swimming around together, and if I send a particle beam into it, what happens if I have, in this case, a beam of electrons, it's going to blow out or expel those plasma electrons. Remember, charges of the same sign repel each other, charges of the same sign attract. So because the electrons in this beam have the same size sign of charge as the plasma electrons get blown out, the beam passes through, and then the ions which were left behind, they exert a restoring force which pulls those plasma electrons back in, and you get this space charge or Wakefield set up behind this beam that looks a lot like the wave behind a boat. And so it turns out, if I take this process one step further, I can actually probe that structure using a single beam, or if I want to make an accelerator out of it, I actually take two beams and send them in. This first beam does all the work. It sets up this Wakefield structure in the plasma. Then I send another beam in behind it, and it rides the wave just like a surfer and gains energy at a very fast rate. So really what we're talking about is a complete paradigm shift where now instead of accelerators and technology that are tens of kilometers to build, we're talking about shrinking that down to something where all the energy boost is done in less than a kilometer, so that now the accelerator itself is not even the dominant instrument when it comes to building an accelerator of the future. So this is really a game-changing technology we're looking at. Now, we should not be afraid to dream big and have big aspirations. In fact, Stanford has a tradition of this. Here's a picture of Professor Hansen down on the Stanford campus about 60 years ago, where this is one of the early prototype structures before the SLAC linac structures, where they were very proud of the fact that this structure was so small that they could fit it on their shoulders, and they used this structure to make electrons, which were about 4 MeV of energy. And in fact, they were so proud of this, they submitted one of the most beautiful reports to the Office of Naval Research, where the entire report said, "We have accelerated electrons." Well, fast forward 60 years later, we're now talking about in the same space, here's one of our early plasma accelerators, we're inside this tube, not adding 4 MeV of energy to the beam, but adding 40 GeV of energy, so 40,000 or 10,000 times the energy gain in the same amount of space. So this all started back in 1997 with this proposal to do a 1 GeV beam acceleration in a 1 meter long plasma cell at the SLAC linac. So actually the first ideas of how you might use plasmas to power accelerators were thought up back in 1979 and 85, but it wasn't until people really realized, let's take this enormous tool that we have, the SLAC linac, and apply that to powering plasmas, that maybe we can start getting fields that are really interesting for high energy physics and these other applications. So I actually came here as a postdoc to work on this experiment back in 97, and I've officially become an old man at the laboratory, because now I can talk to the students in my group and tell them, back in my day, we did experiments in a truck trailer, So this was literally how it all started. You guys are used to reading press releases where everything's done, you've seen the final result, but things start slowly. So we literally pulled up in the central research yard, we started in a truck trailer, we had computers, monitors, data acquisition systems, and slowly over time, we built up our own laboratory where You can't even see the beam line where the electron beam's coming down the pipe. We added a plasma source, a laser system, all sorts of optics, diagnostics, and much like maybe a bad relative that comes and moves in and never leaves, we brought all our stuff with us. But we built up this very sophisticated laboratory and things started to happen. So what was the first result we saw when we sent the beam into the plasma? Well, not surprisingly, it didn't work the first time. So the very first thing we saw was actually we made a mess out of the beam. We sent the beam through the plasma, it hit one of these profile monitor screens down by the dump, turned into a big fuzzball. It was always kicking over to the side. But we were cheering. We were like, yes, we did something. So it turns out that was actually captured. This was a plot we made for the 8 o'clock meeting in the main control center the next day. And what this is a plot of, it shows the deflection that the plasma produced as a function of the density of the plasma. And it was a result. We measured something versus something, and it was a process that allowed us to start understanding what's going on. In fact, this is really okay because oftentimes in experiments, you learn as much from your mistakes as you do from, when you conceptualize and visualize things going forward. So eventually we realized, well, why was the beam getting kicked over to the side? Well, it turns out all the guys that came from the university, this was our view of what a particle beam from an accelerator looked like, where if you're looking at the beam coming down the pipe from the side, you would imagine it's this perfect thing that gently tapers off in all directions. It's straight. It looks magically perfect every time. Well, then when you talk to the guys that actually make the beam in the accelerator, they said, no. It can oftentimes look like this. And that's because over the course of this 3-mile or 2-mile long accelerator, any imperfection in the orbit down the length of the accelerator can cause the front of the beam to talk to the back of the beam, and sometimes you can get this curvature, this shape on the beam where we say it has a tail in the distribution. And what happens is when you send a beam like that into the plasma, the front of the beam defines the center of the focusing channel, and the particles that come down the pack in the back get a kick, and they were always deflected over to the side. So really progress started to come as each of these two communities learned to speak each other's language, and actually very quickly progress started to happen. So once we straightened the beam out, the very first thing we observed was plasma focusing. The plasma makes very strong fields on the beam that you can use to not only gain energy very quickly, but you can use to focus the beam very strongly. So the first thing we noticed was plasma focusing, where here's an image of the beam. This is just up and down, left and right. You stick in what's called a profile monitor so you can measure the transverse distribution of the beam. And when there's no plasma in place, the beam looked like this. And then you put the plasma in place and boom, the plasma grabbed the beam and pinched it very hard and focused it on the screen. And then because we're scientists and we want to understand things, we start changing parameters. In this case, we changed the plasma density and we'd measure the beam size. And the first thing we realized is that, in fact, this plasma focusing is incredibly strong. It's thousands of times stronger than what we can do with the conventional magnets on the beam line. So we developed a model to then understand how strong is the focusing and how should we prepare the beam so that we inject it in the plasma, it'll propagate in a stable condition and not have its beam size change very rapidly. And so that was the first big result that we did. We understood these focusing processes, and now once we had that understood, we were in a condition where we could prepare the beam, inject it in the plasma so that hopefully now good things would happen and we could measure the properties of the plasma in terms of accelerating particles. So in fact, we did that. Here's one of the journals that physicists love to publish in, Physical Review Letters. We actually got the cover. So here was the beam with no plasma. This is where it's now been. We've used a magnet to disperse the beam according to its energy. So low energies are down here, high energies are up here. And then when we turn the plasma on, what we saw is for this single beam, the particles in the front of the beam start losing energy into the plasma wake, and they lose energy and are dispersed down here on the bottom of the image. And then the particles that were in the back, they saw this huge accelerating field, and they got boosted up by a large amount of energy in a short amount of space. And in fact, we broke the GeV barrier for these experiments for the first time, where we now gained more than a GeV in a little tiny accelerator that could fit on this podium. And we were quite proud of that. And in fact, not very long afterwards, we started making the plasma longer, and very quickly the energy started going up and up and up. We were very happy about this. So these set of experiments in the FFTB down at SLAC concluded back in 2006, published in 2007, with something where we did a set of experiments where we ran the linac flat out. We took every klystron we had available. We boosted the energy all the way up to 42 GeV coming out the pipe at the end of the linac, and we sent it into a plasma. And here's a computer simulation of the process that was going on, where the beam comes into the plasma. Again, those plasma electrons go streaming out, come back in, and this inrush of plasma electrons makes very large accelerating fields back here, which in fact doubled the energy of some of those plasma electrons in just a few feet. So imagine that. It took 3,000 meters or 2 miles long of accelerator to get to that 42 GeV, and then in just a few feet we doubled the energy of some of those particles. So this was a real fantastic result for us. But the better is the enemy of the good, and at that point, you guys all may know that the LCLS was coming along, so we had to pick up our stuff from the central research yard and move a couple kilometers upstream and relocate here at Sector 20 in a new facility called FACET. And with FACET, we wanted to build on all that experience we had gained in the Final Focus Test Beam facility and answer our next set of questions. And to help sort of introduce the two big results we got at FACET, I'm going to take advantage of the very nice materials that the communications group helped us throw together for two of our press releases. So I'm going to play the first of two movies right now.
The following animation shows the process of plasma Wakefield acceleration, a promising technique for building more compact and powerful particle accelerators. A plasma is a state of matter where negatively charged electrons and positively charged ions flow freely. At SLAC National Accelerator Laboratories' FACET facility, a thin filament of plasma is created by focusing a powerful laser through an oven filled with lithium vapor. Two bunches of electrons, separated by only about the width of a human hair, are accelerated by SLAC's linear accelerator and sent directly through the plasma filament. The front, or drive bunch, acts like a plow, pushing the free-floating plasma electrons out of the way and creating a wake. The flow of the plasma electrons in the back of the wake create a strong electric field called the plasma Wakefield, through which they transfer their energy to the trailing electron bunch. The result is a method of providing a highly efficient energy boost in a short amount of space. Now let's look at an actual simulation of plasma Wakefield acceleration. In recent experiments, researchers used this technique to propel electrons to energies 400 to 500 times higher than they could reach over the same distance in a traditional particle accelerator powered by microwaves, and with a remarkably high efficiency of roughly 30%. Current experiments work to fine-tune the spacing and shape of the electron bunches. With modest improvements, plasma Wakefield acceleration could provide a basis for a new generation of shorter and more powerful particle accelerators.
Okay, and so one of the things you may have noticed in that video is that it showed two bunches coming into the plasma. Now, all of the results I talked about to this point used a single bunch, because at this point the big questions were, can we make these big fields in a plasma? Will they sustain themselves over a meter distance, or will something go unstable and the whole process break down? So prior to FACET, we used a single bunch that would go into the plasma, and some of the electrons would drive the wake, some would sample the wake, but you get these distributions coming out that had big energy spreads and are not something that you're going to use for some end application. So one of the improvements we wanted to make at FACET was to actually figure out a way to send two individual bunches into the plasma so that one bunch could drive the wake and another bunch could get accelerated cleanly out the back. So we did that by developing a capability to, as we focus and squeeze the particles down all along the length of the accelerator, at some point during this process where we're squeezing them down to make them very short in time, we developed a special system of a collimator. And all this thing is it allows us to chop the distribution in half so that what we would be left with, instead of a single bunch to go into the plasma, is two different bunches, which we could then change the spacing of and the amplitude of the two different bunches, send them into the plasma. Now, to give you a sense of the dimensions that we typically use in the accelerators, most people may not realize, is that these are dimensions on the order of the size of a human hair that you heard in your video. Or when those things are coming down the pipe at the speed of light, these things are a few hundred femtoseconds apart in time. That's a millionth of a billionth of a second. So incredibly short durations in time. So when we add this chopping technique and split the two beams up in two, next question you can say is, well, did it work? Did we get the two bunches we want? And what does it look like before it goes into the plasma? So fortunately, we have a lot of talented people here at SLAC. We had a whole group in the engineering department which they designed and built this beautiful 1 meter long structure which did not add energy to the beam, but instead applied a field which streaks the beam transversely, and it kicks the beam very hard with a time varying field. So what that means is if you now stick in a screen and look at the beam downstream, this beam gets swept vertically across the screen so that the vertical axis up and down is proportional to time. And so you can see that when there's no collimator in the beam, we get a single beam distribution. Then when we added this special chopper to slice the beam, we get two different beams where we can control the spacing and make them just right for these plasma experiments we wanted to do. The second thing we needed was a plasma source. So you may ask, well, is a plasma something you can't go to Walmart and buy a plasma source. So we had to develop, how do we make meter-long plasma sources that were appropriate for these experiments? So our colleagues at UCLA actually figured out a very old technique which they applied to these experiments, a device called a heat pipe oven. So what it is, imagine I have a stainless steel tube here, and on the inside of the tube I have a mesh or a wick which is lining the inside of the tube, and I stuff this full of solid lithium, and now I start heating it up. Well, eventually the lithium melts and starts to cling to this wick on the inside of the pipe. And as I heat it up hotter and hotter and hotter, eventually to about 1,000 degrees centigrade, you can see it's actually, if you look end on, it's glowing red hot inside this thing. But at that point, there's now a column of lithium vapor in the inside, and I can control the density and length of this column of vapor and use that as my plasma source. The second piece I need to add is ionizing that vapor. So we add a laser system that we focus in a special way that ionize and make a preformed plasma down the middle of this plasma source. So now when we put all those pieces together, we put the two beams that we've created in that special chopping technique with this plasma source together, really good things happen. So now here's the two beams coming into the plasma, where again we've used a magnet to disperse them according to energy on this axis, and initially the two beams have almost the same energy. But then when I turn the plasma on, the beam in the front does its job, it pushes out all the plasma electrons, it sets up this big wave in the plasma and loses energy in the process, so it's dispersed low in energy here. But now you can see that the beam that followed behind it now gains energy at a rapid rate, but also all these particles, when the conditions are right, they gain energy at the same rate. And that's important, so that as I now make this accelerator longer and I build this further and further, I now have a distribution of particles that all have roughly the same energy, so that if I want to use that in the future for a collider or an FEL, it's starting to look like it's got the properties of a beam, not just a streak of electrons. And in fact, this was a very important and big result for us. It got us the cover of Nature magazine. And in fact, now one of the things we've been doing at FACET is pushing this further and further, making the plasma source longer and optimizing the two beams we send in. And in fact, we've now shown that we can have these particles gain up to 9 GeV in, again, a plasma that's only the size to fit on this table. And so that's a really fantastic result for us. That's what we're doing with electrons. We're trying to push this technique and push the plasma sources longer and longer, optimize the energy gain we get while preserving the energy spread. And then when I talk about FACET-II a little later, I'll talk about how we're working on the beam quality as well. So now for the second and final movie, I'd like to talk about, there's something you may have been asking, well, what about positrons, you know, the other half to the electrons? And so now one more movie to help introduce what we're doing with positrons.
Researchers use large and powerful particle accelerators to study nature's fundamental particles and forces in particle collisions. In 2012, for instance, scientists discovered the Higgs boson in collisions of two proton beams at CERN's Large Hadron Collider, or LHC. Since protons are composite particles, collisions at the LHC are very complex and difficult to analyze. Therefore, particle physicists plan a next-generation collider that would smash elementary particles into one another, electrons and their antimatter siblings, positrons. However, current technology would require accelerators that are tens of kilometers long, and researchers are looking for alternatives that shrink the size of colliders while accelerating particles to increasingly high energies. One promising approach is plasma Wakefield acceleration, which has been shown to work efficiently for electrons. This approach uses pairs of electron bunches. When an electron drive bunch, brought up to speed in SLAC's FACET facility, enters an ionized gas or plasma, it creates a plasma wake that researchers use to focus and accelerate a trailing electron bunch. For a positron bunch following an electron or positron drive bunch, the situation is much more challenging. No matter where the researchers place the trailing positron bunch, it would experience defocusing in the wake field. Depending on the location, the trailing bunch would also slow down. Now, researchers have found a new method to speed up positrons. Instead of using two bunches, they found that a single positron bunch interacts with the plasma in a way that the bunch head creates a wake field that is accelerating and focusing for the bunch tail. Plasma Wakefield acceleration for electrons and positrons could be used one day to build collider structures that are 100 to 1,000 times shorter than current designs. Even before then, they could potentially be used as a small-scale add-on to existing or future linear accelerators, boosting their energy and collision power.
Had to leave the sound effect. All right, so you may be asking, you're like, what? Yes, we make antimatter SLAC. We do it all the time. Now, truth be told, the beams of antimatter we make are incredibly special, and we'll talk about that in a second. But to give you some perspective, we're not powering the Starship Enterprise just yet. You know, the total amount of antimatter we've made in the history of the laboratory is probably less than a grain of salt. So it's not a lot in terms of physical stuff, but it's got a tremendous amount of power, and it's something that's allowed us to do a lot of neat experiments. So anyway, you may be wondering, how do we do that? So here's a sort of a cartoon or a schematic of what the accelerator looks like, all the individual pieces for the first 2 kilometers that we use for FACET. So there's an electron source, which is out west near where the lab intersects Whiskey Hill and Portola Road. And then the accelerator, the beam progressively builds up energy and is compressed and made short and then focused and made small in all the dimensions and then eventually sent into the plasma 2 kilometers long later. Well, it turns out after the beam's gained almost all of its energy, we have the option to fire a very fast deflecting magnet and kick the beam over into this beam line here. And we can send some electrons into this beam line and then we hit a very dense target, a target that's made out of tungsten and rhenium. These are very heavy, dense materials. And what happens is as the particle beam hits that material, it starts to slow down and it emits a special kind of radiation. There's a German word, braking radiation, or Bremsstrahlung, and it gives off a lot of energy very quickly. And the energy it gives off is in the form of photons, in this case a lot of gamma rays. And these gamma rays can down-convert to other particles like electrons and positrons. So then we use different magnets to separate the electrons and positrons. We collect only the positrons. We give them a little bit of energy, then put them in a beam line, which is actually up in the ceiling of the accelerator down the tunnel, bring them all the way back 2 kilometers upstream, re-inject them into the linac, actually send them into a damping ring where we sort of calm them down, make them behave properly. Then we inject them back into the linac, boost their energy all the way back up, and then we can send them into the plasma and study them here. So be very proud of the fact that SLAC, we really have the only facility in the world that has these high energy, high intensity positron beams that let us probe and understand all this interesting physics. So what does this look like? Now, one of the pictures, the first results I showed you with electrons was the fact that the plasma is focusing for electrons. And it turns out we did, many years ago, the very first experiments with a positron beam in the plasma, and there we found out that things are fundamentally different. When you send the electron beam into a plasma, again, it expels all the plasma electrons and they leave the ions behind, which form a very nice focusing channel for the electron beam. Well, when you send a positron beam into the plasma, it actually draws in all the plasma electrons, and these plasma electrons come streaming in and cross through the positron beam. And what happens is now, depending on where you are along the beam, you see different focusing due to different forces from this positron beam. So now, instead of this cleanly focused image downstream of the plasma, you actually see that some of the particles have indeed been focused very tightly, but other particles have been defocused and they form this sort of halo or cloud around the beam. And this is not good because eventually if you want to use the electrons for something, it means they're not all going to behave in the same way, whether I want to inject them in an undulator or send them into a collider or something. So halo formation is not good. So we already knew back then that we were going to have issues and we were going to have to find a new way to accelerate positrons in a plasma. We couldn't just repeat what we had done for electrons. So at FACET, we had, for the very first time, the ability to make the positrons very short and much denser than we could in those past experiences. And we started doing a set of experiments where we made a high-density long plasma and we sent the positron beam in. And what we found was really interesting, that for the first time, we showed that when the conditions of the incoming beam are just right, we get a very surprising result. If we now look at a beam where now I've dispersed it in energy along the horizontal axis and I look at the electrons coming out, we can see that there's several unanticipated features in what we saw. First of all, the positrons are indeed gaining energy at a very large rate. In this case, they gained about 6 GeV in a 1 meter long plasma, which is fantastic. They had a relatively small spread in energy, also very good. But what was really surprising to us is the narrow divergence of the beam. When we looked at how hard the beam was defocusing coming out of the plasma, it was not defocusing very much at all, and also it didn't have this halo around it. We were expecting to see this cloud of defocused electrons around the outside, and we didn't see that. And this was completely unanticipated, and as we redid the experiment and fed back and forth with our computer simulations trying to understand what was going on, we finally settled in on what was actually happening. So instead of a process where a beam comes in and the plasma electrons get sucked in and then they all flow outwards after the fact and we get these defocusing forces or non-uniform focusing forces, instead what started to happen is that some of the plasma electrons would indeed flow right through the beam and continue on out and then come back sometime later. But some of the plasma electrons would actually stay on the axis. They were mutually attracted to the positron beam. And what would happen is just enough plasma electrons would co-propagate with the incoming positron beam so that now the forces, the positron beam by itself would like to naturally defocus. The plasma electrons would like to make it focus. And so it turns out these two things would settle into an equilibrium state where they would propagate in a condition where they didn't want to defocus, didn't want to focus very much, and they were guided along the entire length of the accelerator. And in addition, the accelerating field, the presence of those plasma electrons would do another nice thing, that it would cause the accelerating field in the plasma to flatten out so that all the positrons gained energy at the same rate, and that explains the narrow spread in energies that we saw. So putting these two things together, this was a fantastic result for us, and it was completely unanticipated. And that was really because in the past we hadn't realized that after some distance into the plasma we could reach this sort of equilibrium state. And so again, it's one of the nice reasons why we do experiments and we study things, because this was not predicted before we started to do the experiments. But we've answered a lot of interesting things with FACET, and there's a lot of questions we'd still like to understand about plasma acceleration going forward in the future. But now we have another issue. So much like before where we had to pick up our stuff and get out of the way of LCLS-1, now we have to do the same things. We have to get out of the way of LCLS-2. And that's because FACET, the facility that uses the first 2 kilometers of the linac, we're actually going to have our final run and turn off in April of next year. And that's because the laboratory has this fantastic new project called the LCLS-2 coming along. So what's going to happen is, after we turn off in April, we're going to go through and take out anything that's useful and can be salvaged out of the first kilometer of the linac. All the accelerating structures, magnets, anything that's useful, we're going to take out of the linac. And then it's going to be put in a state called cold, dark, and dry, so that the contractors can come in, cut up what's left, clear the whole thing out, and they're going to take it down to the walls so that literally the only thing left is probably going to be the light fixtures. So they're going to clean out the first kilometer of the linac and put in this fantastic new superconducting linac. And why that's so wonderful is because the existing 50-year-old linac has got us several Nobel Prizes. It's served the LCLS, FACET, and a multitude of programs and done fantastic work for us. But it delivers electron beams at a rate of about 100 times per second. The new accelerator we're going to put in the front part of the linac is going to deliver electrons at a rate of 1,000,000 times per second. So that's going to completely change what we can do with those beams and make X-rays downstream. So as we do that and get ready to upgrade the first kilometer of the linac, to help us answer the next set of questions that we want to answer for plasma Wakefield acceleration, we're going to build a new facility called FACET-II. So what that's going to look like is we're going to still leave all of our equipment, the plasma source, all of our instrumentation, we're going to leave in the middle kilometer of the linac here out at sector 20. And then we're going to add a new electron source. And this is going to look almost exactly like what LCLS-1 looks like using the last kilometer of the linac. We're going to add a new electron source, and that's going to give us new beams that have new properties, let us answer a new set of questions, and that'll be the first phase of FACET-II. Second phase, we're going to add a new damping ring inside the linac tunnel to allow us to get positrons going again. And then the third thing, which is really cool, is we're going to add the capability called a sailboat chicane. This is a special beamline that'll let us deliver electrons and positrons to the plasma at the same time. So we can do a whole bunch of cool questions with that. And this is the time frame. This is all going to happen over roughly the next 5 years at the lab. So the accelerator that you see now is going to look completely different in about 5 years from now. Now, in thinking about, well, we've done a lot of nice work for plasmas, what would be the next set of questions that we would want to answer with plasmas? I guess, every once in a while we step back and we think, all right, if we just had our way, how could we, in the far future, how could we do something really fantastic and maybe put a bunch of these plasma accelerators together to make a tool for high energy physics? And this was the latest concept of how we thought we might do that. We developed this for something that's called the snow mass process, where every 5 to 10 years, the physics community gets together, thinks big thoughts, and tries to give recommendations to the government about what are the big projects we should do in the future. So as part of that process, we thought to ourselves, all right, what would a collider look like if you made it out of plasmas? And basically what it looks like is a bunch of little plasma cells where each time one of these plasma cells gives about 25 GeV of energy to the beam. And you do that many, many times, and so you get 25, 50, 75, 100. And after about 20 plasma stages, you very rapidly have very high energies that you can use for a collider. And then you power each of those stages with an independent bunch of electrons, which you then create and distribute accordingly. So with FACET-II, we want to answer not only how do we make one of these plasma accelerator stages, answer the rest of the questions for that, but then think about how can we string them together and do it in a way that's compelling, both if we want to accelerate electrons and we want to accelerate positrons. So one of the things that I told you, we discovered this new regime for accelerating positrons where we actually drive the plasma wake with a positron beam. That's very interesting, but it turns out from that picture I showed you before, it'd actually be electrically more efficient if we could actually set up the plasma wave with a beam of electrons and then sample it and accelerate a beam of positrons behind it. Well, to do that, we now have to get around this issue of the defocusing fields from the positrons. So one of the ways we're looking at doing that is creating a special kind of plasma structure where the plasma is not uniform. It's called a hollow channel plasma. And this is actually, the early work on this is being done by one of our PhD students, Spencer Gessner, who's in the audience somewhere. And what it looks like is you can now imagine that instead of making a uniform plasma where the plasma electron density is the same everywhere, I use a special optic which changes our laser pulse so it only makes a plasma which has this special annular shape, and now the beam comes down the middle of the tube here. So essentially the plasma looks like a straw where there's plasma electrons on the outside and no plasma down the middle. So the beam can propagate down the middle of this, and as it does, all these plasma electrons which are out here in the perimeter, they're going to oscillate back and forth, and that's going to give me accelerating fields that I can use to change the beam energy very rapidly. But because there are no plasma electrons inside the middle here, I get no focusing forces. So in principle, I could now send an electron beam through this plasma, get very large accelerating fields, but not have to worry about these defocusing fields from the plasma electrons. So we're doing some of the early work to develop this sort of plasma source right now, but looking ahead to FACET-II, we actually want to now do this for real and show that we can send an electron beam through, excite the plasma wake, and then send a positron beam close behind it and boost the positron beam with a very rapid accelerating gradient. The second thing we'd like to do is I mentioned that if you want to get to really high energies like you need for a collider, you have to think about stringing many of these plasma stages together. So one of the things you'd like to answer is, okay, how accurately do I have to control how I position these two bunches next to each other in terms of how closely they're spaced in time, how accurately I align them together left, right, up, down. So to do that, we're actually going to add an independent injector so that we can send one beam from the accelerator, drive the plasma wake, and then use a different electron source and understand and characterize and make these measurements about just how precisely I have to position the beams with respect to each other. The second thing we'd like to do is take advantage of the fact that accelerator physicists are very creative, that most of the beams we make in the pipe, if you were to look at their profiles, it looks like a bell curve, the same distribution you'd get when you plot grades in a classroom or something. But it turns out we actually know how to make beam distributions where it's not just a Gaussian or a bell curve. It actually has a different shape. And it turns out if you play with the shapes of these beams, you can optimize what you get in the plasma so that you get an energy boost which is much larger than this factor of 2. We can do a lot more than just doubling the energy each time we go into the plasma stage. We get an energy gain of 5 or 10 times the initial energy. So these are things we want to look at by taking advantage of the fact of controlling and shaping the beams independently. The final thing we want to address at FACET-II is not just using plasmas as accelerators, but it's potentially using plasmas to reimagine how we make the electron beams to begin with. So one of the things that makes the X-ray laser, the LCLS we have work, is the fact that people developed this enabling technology called a photoinjector. And what's so important about the photoinjector is it makes a distribution of electrons that have a very good beam quality. And what I mean by beam quality is the focusability of the electrons. That it means if you ask them to do something or move in a certain way, they all are going to move it the same way. And by doing that, when the beams have this exquisite quality, you can get devices like the X-ray laser to work very well. Well, the source for this, these electrons is actually fairly simple to understand. It's an accelerator. It's made out of copper. Here's a picture of it, or a picture of a variant of it. And the way that works is imagine that I have an accelerating structure here that I send in high power microwaves, and those microwaves make these very big fields on the order of 100 megavolts per meter inside the structure. And now I shine an ultraviolet laser onto the copper, and through the photoelectric effect, some electrons come out of the copper, they see this big accelerating field, and whoo-hoo, they gain energy and come flying out the back end of this very quickly. Now the beam size, when it starts off in this accelerator, until we get the beams up to very high energies, we don't want to focus them too tightly, otherwise they push each other apart and you lose the beam quality. So the beam starts off with sizes which are on the order of scales of millimeter and durations on the order of a picosecond, or a millionth of a second. Before we get it to the FEL, we now boost its energy up and try and compress and squeeze these beams down and reduce their dimensions by a factor of 100 to 1,000 in all different planes. And we have to take great care and pains not to ruin the beam quality as we do that. So now take a step back and imagine that, remember this picture of a plasma accelerator that I showed you, where again a beam comes into a plasma, the plasma electrons blow out, and we're left with this little tiny accelerating structure here, where now the fields are not 100 megavolts per meter, but they're hundreds of gigavolts per meter. And the spatial dimensions are already to the point where if I could find a way to release electrons in this accelerator, they would already have the duration and the spatial extent that I want for these other applications. And in principle, there's lots of different ways we're exploring to release electrons inside these plasma accelerators, but in principle, our computer simulations tell us that the beam quality, the emittance, the brightness, these numbers we use to characterize this focusability of the electrons is up to 100 times better than what we can get with the LCLS. Now, why that's interesting is Now fast forward into the distant future and imagine, how could I use plasma accelerators to reimagine what an FEL looks like? And here's one example. There's others, but this is my favorite. So imagine that I take a regular accelerator. It could be normal conducting, it could be superconducting, but I use this to make a beam that has an energy of, say, 500 MeV. So I can do that in about the size of this auditorium. That's the distance that it takes to get a couple of first downs in a football game, and I can make a 500 MeV beam. So not a big accelerator at all. But it's making particle beams that are coming at millions of times per second, and I take those beams and I send them into a plasma where I not only use the plasma to boost up the energy by many, many factors, in this case maybe a factor of 5, but I also use the plasma as the source of electrons. So this is just a power source. I dump the energy into the plasma, then throw these electrons away, and I use the plasma accelerator as a source of an incredibly bright, high-quality electron beam that now comes flying out with much lower energy. And if I could do that, then not only could I make a whole FEL where the whole size of the accelerator is much smaller, but also now because the beam quality is so good, everything gets better. The undulator gets shorter. I don't need hundreds of meters of undulator. I could now do maybe tens of meters of undulator. So I could put all these technologies together to really reimagine how a light source might look like in the distant future. So there's a lot of interesting things that we're doing with plasma accelerators. Personally, for me, this work is a tremendous amount of fun because it, first of all, combines very interesting questions. I've enjoyed the fact that it's done not just by people here at SLAC, it's done between groups at SLAC and universities and other laboratories all over the world. And by putting the unique facilities we have at SLAC, whether it was the FFTB, FACET, and eventually FACET-II, and combining all of these traits, rapid scientific progress has followed. And that's really, it's a neat time to be an accelerator physicist in my view. So anyway, I think it's a really exciting time looking ahead. I think we're making a lot of progress. I think that we've demonstrated many neat things with accelerating electrons and positrons, doing it at high gradient and high quality. And I think in the coming years, we're going to build on this and use the plasmas not only as sources for as accelerators, but also sources of high brightness electron beams, which are really going to pave the way for hopefully the first applications, like maybe 10, 20 years from now, thinking about how we might reimagine the FELs that we make using conventional accelerators. So if you want more equations and more information about how some of these things were derived and want to dive a little deeper, there's a presentation I did this summer which has a lot more information on it. You can get that at the URL down here at the bottom. And I guess with that, I'll take questions. Thank you.
Okay, we have a few minutes for questions.
45, that's perfect.
Does the 1 liter plasma add a certain energy to the drive beam, or does it multiply the drive beam?
Great question. So the plasma itself, there's no energy is conserved, first of all. So the plasma is it's almost like an electrical transformer. So it doesn't provide the energy to the system. All the energy is provided by that first beam that comes in. But one of the things that's nice is, because we've been working on trying to make colliders and accelerators for many, many decades, we know how to make really high current accelerators at relatively low energies. So what the plasma does, it allows us to convert that system to where I can get the beam energy with I can take that system that has high current and low energy and transform it into a system that has a lower current but much higher energy. So it allows us to get the energy of the beams up in a very, very compact space.
Does each section of this longer linac, does it multiply the previous sector by a certain factor, or does it add 10 GeV per meter?
Adds 10 GeV or 20 GeV per meter. So yeah, it goes 20, 40, 60, 80 each time.
Thank you.
What is the typical relation between the charge of your drive beam and the trailing beam?
So it's a little bit of, if you have a Gaussian beam, meaning that the beam distribution is normal distribution going into the plasma, there's a fundamental theory of beam loading which says that the ratio of the deaccelerating field, where I'm sucking energy out of one beam, and the accelerating field that's following behind it, that ratio is never going to be more than 2. So if energy is conserved, if the plasma perfectly transferred the energy from one to another, that would tell you that you have that product that you can play with. If I want to gain more energy, then I have to put less charge in the witness beam. or I can put less charge in the witness beam and have that beam gain energy. It's one of these things where the total amount of energy in the system's conserved. So it depends on how much energy you put into the witness beam, or how much charge you put into the witness beam. So typically for the experiments we do, it's about a factor of a half or a third.
What is the lifetime of the plasmas? What does it mean for your repetition rate scaling?
So the plasmas themselves, there's different processes. You know, you make this plasma, you strip the electrons off, and then eventually the electrons left to themselves, they're going to recombine with the atoms. And this process is called recombination. Now the rate that that happens is dependent upon the plasma density that you use. So for the plasma densities that we use for these experiments, the recombination rate happens on the order of a nanosecond, which is very, very slow compared to the passage of these beams and what goes on with the accelerator. What then starts to happen, though, and one of the questions we have to look at for the future is, as the plasma, you know, all this magic happens, you boost the energy of the electrons, and now there's some plasma with some noise and turbulence left in it. How long does it take for that to completely quiet down before the next set of bunches could come into the plasma? So that's something where we've done estimates on this. It's not clear if it's a microsecond or a millisecond, which means that you could send beams through at either a megahertz or a kilohertz. So that's something where, those are questions we have to answer. We'd like to measure it experimentally, but there's also a question of, you could say, if it's a problem, that now maybe I look at changing the plasma source where there's actually a flow of the plasma so that you don't use the same distribution of gas for the pulse that comes through in the second time, so that you're always changing the gas that you use. Ernest?
How large is your collaboration, and do you have any military sponsorship?
We have no military sponsorship, and that's a whole long story. No military sponsorship. The collaboration right now, you know, FACET actually operates as a national user facility, and if you look at all the experiments we do at FACET, there's about 150 users, 25 different experiments, and then each of those collaborations has anywhere from 5 to 25 people participating in the collaboration. So there's one set of collaborators are working on trying to accelerate electrons. Another group's working on accelerating positrons. Another groups are working on different ways to make the plasmas the source of these high brightness electrons. Now, if you look at the Venn diagram of who those people are, there's many of us, like the people at SLAC and the people that work in my group. We work on all those experiments, but there's different people come in and bring different pieces to the puzzle depending on what precisely the physics is that we're looking at.
Be interesting for high energy physics to have a photon-photon collider with the same type of energy and intensity as an electron-positron collider. Photon-photon, is that a possibility using the plasma techniques?
It is. It's one of these things where the reality is we're not the people to make that case. Periodically, like, when snowmass process was happening, we talked to Michael, who's somewhere around here, and other people, and trying to understand what does the customer and the community want? Do you want electron-positron? Would you want electron-electron? Would you want gamma-gamma? So I think what we heard is that people would by far like to have the electron-positron most, but if they couldn't have that, it doesn't mean there's not physics that you could do with electron-electron or gamma-gamma. And so certainly, that's even easier because now you don't have to worry about the positron piece. So it's one of those things where for now we're trying to dream big and think, can we do all of these pieces of it? But down the road, it may be something where you say, no, the positrons are hard. Let's think about gamma-gamma or something.
Gamma-gamma gives you Higgs production, top quark production, all sorts of nice things. So it doesn't even have to be high energy to get very interesting new physics.
Cool.
You have accelerating mass, so first thing I thought was like a force you might be getting out of here. Can you talk a little bit now things smaller, maybe like a propulsion kind of system for our buddies at NASA, JPL, things like that? Is that possible? Or?
Well, it is funny. There are people that plasmas are interesting because almost anytime you put a lot of energy into a system, very quickly you pull the bonds apart and you make this state of plasma. Now for thrusters, for spacecraft and stuff, there's two different regimes. Doesn't really apply to what we're doing here, but there's one regime for satellites where you need actually just very small amounts of thrust because you're just correcting the orbit of a satellite, and there they actually use, a friend of mine was telling me that, well, there's flavors of plasma thrusters where it's really not a lot of plasma you're making and not very frequently. Then there's other people envisioning how could you basically expel a lot of stuff as a rocket out the back, like the Vasmer engine, and There's several people working on this. There's plasma physics similarities between that and what we do, but otherwise it's sort of, yeah, it's a plasma, same densities, temperatures, but here mass isn't so much moving around as that we're changing energy. Energy's changing hands, so we're not really expelling mass one way or another. We're just transferring energy.
Thanks.
Are there any new safety issues with these higher level energies? Any kind of shielding or things that you see that need to be improved? Or
thank goodness, in the end, before we do any sort of experiments, thank God we work with our colleagues in the radiation physics department to simulate how we're going to dispose of the electrons down the tunnel. Fortunately, any sins we're going to commit have long since happened in the accelerator tunnel, and that's because if you look at the history of the way the lab was built, what really matters is it's sort of a combination of the energy of the particles and the number of the particles you had, the total power that's stored in the beam. And back when the beams were first made in the 60s, they didn't have as high of energy, but there were a lot of them coming down the pipe. And so the total beam power was much higher than we're using right now. So when we designed FACET, we designed the beam dump and stuff to accommodate electrons that would have huge spreads in energy. So we do dump the electrons and dispose of them. But in terms of radiation shielding and down in the tunnel, we're adequately protected.
All right, thanks, Mark. Once more.